If you rode in an early automobile, you felt every single rock, rut, and dip in the dirt. Without a mechanical system to filter physical vibrations, the rigid structure of the carriage transferred the chaotic energy of the road directly into the passengers. To isolate the vehicle body from those violent inputs, engineers developed the modern suspension system. As we see in this image, it relies on two primary mechanical components: the heavy blue coil spring and the central shock absorber strut. When the car hits a bump, three distinct forces react. First is inertia. The sheer mass of the heavy car body inherently resists sudden changes in acceleration, preferring to stay exactly where it is. Second is the restoring force of the springs. The moment the wheel is pushed upward, the spring compresses and pushes back to restore the car to equilibrium position. The further it compresses, the harder it pushes. Third is the damping resistance of the shock absorbers. If the car relied on springs alone, it would bounce endlessly. The oil inside the shock struts pushes back against the movement, and this resistance increases proportional to the velocity of the bounce. We can balance these three internal forces using Newton's second law, resulting in this second-order linear differential equation. The mx double dot term represents inertia. The x dot term represents shock damping. The standard x term represents spring stiffness. On the right side of the equation, F of t is the driving force. This is the physical road surface itself, a continuous, unpredictable stream of upward and downward pushes against the tire. Calculating how a car responds to a single, isolated bump is straightforward, but when you try to solve this calculus equation for a continuous, chaotic road surface, the math becomes analytically intractable. When a car wheel hits a deep pothole, the suspension compresses in a sudden, violent jolt. We call this immediate reaction the transient response. Engineers largely ignore this transient response when they analyze overall ride quality. Because of the damping provided by the shock absorbers, the solution for this jolt always includes a decaying exponential. The energy dissipates and dies away quickly. What matters for passenger comfort is the steady state. This is the continuous, forced vibration that remains after the initial jolt settles down, like the rhythmic thumping of driving over highway expansion joints. Here is the mathematical roadblock. Calculating the steady state in the time domain means solving a differential equation by integrating complex, non-repeating road patterns over time. The calculus quickly becomes a dead end. To solve this, we use Fourier dynamics. Instead of dealing with the messy, irregular shape of the physical road, we break the chaotic input down into a sum of simple, repeating sine waves. By doing this, we bypass the trap of complex time domain calculus. We stop trying to track the suspension's movement second by second and translate the problem into pure geometry. To avoid calculus, we make an assumption. Both the chaotic road and the car's resulting motion can be reconstructed perfectly using the exponential Fourier series. The fundamental building block of this series is Euler's complex exponential, e to the power of in omega t. Look at the variable t inside the exponent. This represents linear time, advancing steadily forward along a one-dimensional axis. The geometry of the equation maps that forward progression of time onto a vector of length 1, rotating continuously in a perfect circle on the complex plane. As time t ticks forward constantly, the phase of the rotation advances periodically. The exact speed of that rotation is determined by the frequency variable, n omega. This specific mathematical term acts as a bridge. It takes a continuous one-way progression, time, and successfully maps it onto a repeating periodic cycle of kinematics.
Representing motion as a complex exponential turns differential equations into algebraic ones. We start with our baseline position equation. When we take the first derivative to find the velocity, differentiating with respect to time simply pulls down the constant from the exponent. The velocity, x dot, is now just in omega multiplied by the original term. In physical reality, this tells us that as the frequency of the road bumps increases, the mechanical velocity of the suspension gets exponentially larger. To find the acceleration, we take the second derivative. This pulls down another identical factor of in omega. We multiply the terms together, resulting in I squared, n squared, omega squared. Because I is an imaginary number, I squared simplifies to -1. This flips the sign of the acceleration term, leaving us with negative n squared omega squared. We have entirely erased the need to perform integration. Every difficult derivative in our physical model has been replaced with a simple, scalable algebraic factor. Now we use a substitution engine to merge our new algebraic rules back into Newton's original physical law. Here is the differential equation governing our suspension system. First, we replace the calculus-based velocity term x dot with its new algebraic equivalent, I n omega. Next, we swap the calculus-based acceleration term x double dot with its exact algebraic equivalent, negative n squared omega squared. Look at the left side of the equation. Every single term now shares the exact same complex exponential baseline. We can group these together and factor out the common term. This brings us to the principle of linear independence, or orthogonality. For two Fourier series to be equal to each other, they must be equal at every individual frequency independently. Because of this rule, we can completely drop the summation symbols and the complex exponential terms from the equation entirely. We stopped trying to solve how high the car is at a specific second in time. Instead, we are solving how a single pure note of the road produces a single pure note of vibration. By rearranging the equation, we isolate the final algebraic ratio of output to input. This is the transfer function, the mathematical DNA of the physical system. The car's behavior is determined entirely by the denominator. At low frequencies, the stiffness term dominates, and the car follows the road. At high speeds, the massive inertia term drives the overall output to zero, unable to match high-frequency chatter. The danger zone is resonance, where the car's natural frequency matches the road's. The stiffness and inertia terms mathematically cancel out. Now only the imaginary damping term prevents the denominator from hitting zero. Without shocks to dissipate energy, the vehicle shakes apart. Engineers treat the suspension as a tunable mathematical filter designed to block specific vibrational frequencies. How do we take these isolated frequency numbers and reconstruct the actual bumpy ride the driver feels in the real world? We use superposition, like a summation funnel. Each colored dot represents a specific frequency response. We drop these filtered components into the funnel to add them together. Out the bottom comes x of t, a continuous wavy line representing the final real-world motion of the car. This process grants engineers the power of predictive design. You can change a shock absorber's stiffness mathematically, run the new variable through the transfer function, and instantly see how the new ride quality feels. By translating a chaotic time domain problem into pure frequency domain algebra, engineers tame physical reality. They ensure the suspension filters out the road's violence,